Hey guys, we are going to take a look at this thing called science. And sometimes people call this the scientific method. And we're going to break it down and try to take it apart and then try to put it all back together again so that you guys can understand what this approach to answering questions is all about. All right. Now, before I go any further, I just want to make sure you guys understand that science is not the oldest and it's not always the best way of getting answers to your questions. Okay. Science is like a screwdriver, it has a very specific job. It does some things really well, and it does other things terribly. All right. So if you want to get questions, or if you want to ask questions and get answers about stuff that are coming from how you feel and what you should do or what you shouldn't do, science usually isn't the best way to get that question answered. There are other ways that humans have come up with to answer those types of questions. But science is really good at answering questions about how the world works, okay, and why things are the way they are, okay? That is what science does really well. So keep that in mind. Okay, science is a tool for answering questions, and humans, by our very natures, we are questioning creatures. We have what are called inquisitive minds. We're always asking questions about why is it this way? How does that work? Where did that come from? When is this going to happen? This is just the way our brains are built. Okay, so when you talk about a scientific answer, you're talking about some really specific criteria or characteristics of a scientific answer. Okay, science is an answer to a question that's supported by observations that different people have made in different places. Okay, it's supported by repeated observations, and science actually is not a place where you are influencing what you're thinking and what you're saying by what you hope for or what you wish for or what you believe in. Science tries to be objective, not subjective. It tries to answer questions in ways that produce answers that are correct or repeatable across time and space. Okay, so enough about that philosophy. Let's get into it. All right, so science is based on observations and experiments. And for this class, you guys really need to know how experiments are built, which is done using a method called the scientific method. Now, I can't give you step one, step two, step three, step four for this, all right? Science happens in lots of ways. Science sometimes happens completely by accident. So I'm going to try to break it down into ways I hope are the most useful and make the most sense. Okay, so a good place to start is with a good experiment. What makes an experiment good? Okay, well, an experiment is going to test a variable. Now, a variable is something that you can change. Okay, so you can make it bigger, you can make it smaller, you can make it more, you can make it less, you can make it this, you can make it that. But by being a variable, that means that it can change. It has the ability to change. And a good experiment is going to test one variable at a time. And this variable that you're testing, that you get to set up, is called your independent variable. It's kind of the starting point. Okay, so the independent variable is also known as the IV. You get it? Independent variable, IV. And you can think of it as a stimulus or a cause. Okay, now the other variable that you need to do an experiment is something that you can measure. You can think of this as something that happens or a result or an effect. This is called the dependent variable or the DV. Okay, so the IV causes the DV. All right, you can think of the dependent variable as a response or an effect. Okay, now we can put this into a statement that some of you probably are already recognizing, something called a hypothesis in an if-then statement. So if I do this, IV, then I'm predicting DV will happen. Okay, so built into this framework, after the word if is the independent variable. That's the variable you are setting up. And then, after the word then, is your dependent variable. That's what you're going to be measuring. That's the effect that you're predicting is going to happen. Okay? Now, lots of people get into trouble when they use the word theory when they really mean hypothesis. And this is perfectly fine in everyday English conversation or conversation in any language, all right? I only really know English, so I can't give you the other versions of this. But a theory, okay, is completely different in science from a hypothesis, okay? A hypothesis is what you think is the reason for something happening. It's a reasonable guess or explanation for something that you're predicting, okay? And it's reasonable. Now, to be a scientific hypothesis, it has to be something you can actually test. You can't just say, I think this person is like that because they're evil, okay? There's no way to test evilness. That's not a science thing. So the idea here is your hypothesis has to be testable, all right? And it must be testable over and over again. We call this repeatability, all right? So if your hypothesis is testable, you can set up your experiment and do it over and over again, all right? Then it's a good hypothesis, irrespective of what happens, okay? So a hypothesis is good if it's reasonable, if you can test it, and you can test it over and over again. It's not limited to just one point in time. All right, a theory is what happens to a hypothesis when it becomes accepted. Okay, now a theory is a good hypothesis that's been supported by multiple sources of data, usually over an extended period of time. So a theory is what you want your hypothesis to turn into. Okay, so once you do your experiments, and no matter how many times you do it, it comes out to the same answer, then your explanation, your hypothesis, becomes a theory. We consider it to be factual. Okay, so in science, or especially in biology, a theory is equivalent to a fact. Okay, now theories must be supported by most of the data. Okay, so different scientists working in different fields of study get information that all points to the same explanation. That is the hallmark, or that's the indication that you have a good theory. Okay, theories should be pretty good at predicting outcomes that haven't been tested yet. Okay, so theories, the usefulness of theories is they allow us to actually make predictions sometimes that are pretty accurate about something that hasn't happened yet. Okay, and always keep in mind, theories can actually be thrown out if new data comes up or a new science is invented that proves them wrong. Okay, so a theory can be thrown out at any time. Okay, there's nothing magical about them. Actually, science is a highway littered with the wreckage of old theories. Let me share with you a few of them. So here are some old, dead scientific theories. Okay, the world is a solid ball of rock. Okay, before most of the way through the 1800s, most scientists, now I'm saying scientists here, believed that the Earth was a solid ball of rock, and that if you found a cave system that went deep enough, you could actually travel from one side of the Earth to the other by going through the center of the Earth. There were some great sci-fi stories written about this. Journey to the Center of the Earth is one of them, and I think that was written by Jules Verne or H.G. Wells. I forget. But not true. We now know that the Earth is partially solid and partially liquid, depending how deep you go. Here's another one. The sun is a ball of burning material. Okay? In the 1700s, the only explanation people had for bright, hot things was a fire. Okay? So people looked up at the sun and they said, oh, the sun must be a big ball of burning something. We now know that's not true. There is no fire on the sun. The sun is doing a lot of things, but it's not burning anything, all right? Excuse me. Okay, let's do a couple more, okay? X-rays are harmless. When X-rays are first discovered, scientists got all excited because X-rays can go through things that light can't go through. So X-rays were used to show the bones in people's feet, the bones in whole bodies. Scientists didn't discover until much later that X-rays are actually pretty harmless, pretty harmful, especially at high dosages. And finally, my favorite, nicotine helps your lungs breathe in more deeply. People have been smoking cigarettes, oh man, since the 1500s. Okay, tobacco became very, very popular around the entire planet, and people actually smoked cigarettes or used tobacco when they had lung problems because it thought it made their health better. Okay, not true. Unfortunately, not true. Nicotine does a lot of things, and a big part of what it does is it damages your lungs. Okay, so these are some old dead theories. Theories are dying and being tossed aside all the time in science. Science is constantly changing. Okay, it's never set in stone. Okay, let's do an example and play around a little bit with scientific method. Okay, so I'm hoping you guys know that fertilizers are chemicals that can make plants grow better. People buy fertilizer to put on their gardens or put on their lawns to make their plants grow better. I think you guys know that, all right? So let's turn that into a hypothesis. If I give plants fertilizer, then they will grow bigger. They will grow larger, okay? Now you'll notice after the word if is give plants fertilizer. There's your IV. And after the word then is they will grow larger. There's your DV. Okay, so the IV is the fertilizer, the independent variable, what you can control. And the DV is how big your plants grow. That's what you're measuring. Because remember, the IV is what you're controlling, and the DV is what you're measuring. All right, so we could design an experiment based on 10 plants, and we're going to give them different amounts of fertilizer, and we're going to measure how they grow. A really simple little experimental design. All right, so let's play around with that idea and let's play around with some graphs and some tables. Okay, because the way that I am going to understand or figure out or measure, if you will, how much of this you guys get is you're going to see tables and you're going to see graphs and you're going to be asked questions about them. So you have to be able to read data, which is just measurements, in a table or in a graph. All right, so let's do a table first. Okay, so imagine we have 10 plants. So I'm going to label one column of my table plants, and I'm going to number them plant 1, plant 2, all the way down to plant 10. Okay, now if you guys remember, we're going to give some of these plants fertilizer. Okay, so let's make our second column how much fertilizer we give them. So we're going to give plants 1 and 2 no fertilizer. There's a reason why we're doing this. I'll explain it in just a few minutes. Plants 3 and 4 are both going to get 1 gram of fertilizer. Plants 5 and 6 are going to get twice as much. They're going to get 2 grams of fertilizer. Plants 7 and 8, I just decided to do this because this is my independent variable. I have control. I'm going to say, okay, for plants 7 and 8, I'm going to give them twice again as much fertilizer. So I'm going to double 2 into 4. Okay, and finally, for plants 9 and 10, I'm going to double it 3 times, and I'm going to give them 8 grams of fertilizer. All right, now, what you choose to do here is completely independent. It is up to you. That's why it's called the independent variable. All right, now, we are going to grow these plants under the exact same conditions because we only want one independent variable. So we're going to set up this experiment with all kinds of constants. For example, we're going to give all these plants the same amount of water, the same amount of light, the same temperature. We're going to use the same kind of plant or the same kind of seeds, etc. These are all called constants, and they're going to be exactly the same for all plants, 1 through 10. That's really important. All right, I'm not going to make a separate column for each of these. You could if you wanted to, but they're all the same. So I'm just going to put here all exactly the same. Okay, now we are going to measure how much these plants grow. So this is our DV. Okay, so we're going to measure how much they weigh. Now in science, we talk about weight as mass. I'm just putting weight here because that's probably the word you're more familiar with. But I don't have any data yet. I haven't actually done this experiment. I'm actually making this up right now, just as an example. So I don't have any weights. So I'm just putting question marks there. It doesn't matter. All right. So the IV is the amount of fertilizer. That is what the scientist is choosing or controlling. That's where it gets its independence. Okay, so in this example, the amount of fertilizer is what we call the independent variable. Okay, the constants, these are the things that you don't allow to change. Now, we could change a constant like temperature or amount of water or amount of light or type of plant. But if we do that, we turn that constant into another independent variable. And generally in science, you don't want to do multiple independent variables in the same experiment. You want to keep them separate. You want to keep your IVs down to one thing. And in this example, it's the amount of fertilizer. Okay, and finally, weight is something that we can easily measure. So that's a really good dependent variable. So it's dependent on what the independent variable is doing. So that's why it's called the DV, or the dependent variable. All right. Okay, so we got IV, we got constants, and we got DV. And we got some different numbers here for some different plants. Okay, now, if you notice, plants 1 and 2, they don't get any fertilizer, okay? Because we need, to do a scientific experiment, we need what's called a control group, okay? The control group does not have the IV. It's always missing the IV, okay? All good experiments need a control group. So we need to grow a couple plants, at least a couple plants, that don't get any fertilizer, because that's kind of our baseline or our starting point. We need the control group to compare to all the other plants. Okay, so it's always important to have a control group that does not have the IV. So you'll see here that plants 1 and 2 have 0 grams of fertilizer. So they don't get anything but the water, the light, the nice warm room. Okay, they get the constants, but they don't get the IV. Okay, plants 3 through 10, okay, are what we call the experimental groups. Okay, now you'll notice there are 2 plants for each IV. For example, plants 3 and 4 both get 1 gram each of fertilizer. So whenever you are repeating, okay, or doubling or tripling or quadrupling the same IV in an experiment, those are called trials. So we have 2 trials for each IV. Okay, plants 1 and 2, that's our control group. 3 and 4, that's our first level of IV. 5 and 6, that's our second level of the independent variable. 7 and 8, third level, and 9 and 10, fourth level. So we're doing 4 different levels of the same independent variable. Okay? All right. So it is a best practice to do as many trials as you can. The more trials, the better. Okay? Fewer trials is worse. Now, the advantage of doing more trials is, what if plant 1 died? Okay? Just randomly, plant 1 got sick and died. Okay? You don't have any data for that independent variable. But if you have 2 trials, if you do 2 plants that don't get any fertilizer, then your experiment is ruined. Okay? Next example, if you do multiple trials, you can average your data. Okay? We do this all the time at school. Okay? We don't just give you one big test at the end of the year to figure out how much you learned. Okay? We give you lots of assignments all along the way, which are trials, to figure out, and then we average all that data to come up with your final grade. So if you have more than 1 trial, you can average your data. And averages are always a better reflection of reality than a single data point. Okay? I like to think of it this way. I'm a pretty crappy bowler, bowling where you roll the ball and you knock over the pins. So if I bowled 1 game and I happened to score really well for that 1 game, I just was lucky, that doesn't mean I'm a good bowler, okay? You want to get the average. So I might bowl 10 games and then average my scores. And that's going to be a better reflection of how good of a bowler I am. So averages are always better, okay? If you do multiple trials, you can do averages. And multiple trials allow you to compensate for accidents, for things that happen that you weren't predicting, okay? Like a plant dying. All right, now, making a graph. Oh man, I deal with this all the way from freshmen all the way up to seniors, okay? The ability to draw and label a graph is something that's almost always worth a lot of points in all science classes. Okay? Now, graphs are wonderful because they show you what's happening as a picture, not as a table of numbers. They're visual representations of data. Okay? And somebody a long time ago said a picture's worth 1,000 words. Okay? Humans, we're very visual creatures and we like to look at pictures. Not very many people like to look at columns of numbers. Okay? So graphing is better. A graph allows you to see trends. Are the numbers going up? Are the numbers going down? Are they going up and then down? These are what we call trends. Okay? Graphs are easier for you to see what's important. What jumps out at you? Oh, wow, plant number 6 really changed a lot. Okay, that's going to jump out at you on a graph, but you might miss it in just a table of numbers. All right, so how do you make a graph? Well, the independent variable should always be graphed on the x-axis. Okay, and the x-axis is the part of the graph that runs horizontal or flat across. That's where your IV data is going to go. Okay? The DV data should always go on the y-axis. That's the part of the graph that goes up and down. Okay? That's pretty much a rule for science. Now, newspapers and magazines, they publish all sorts of graphs that move things around. That's perfectly fine, but for this class and for chemistry and for physics, make sure you keep your IV on the x-axis and your DV on the y-axis, okay? That's the standard for science, okay? You're going to use a line graph most of the time, but only if the independent data is what we call continuous. Okay, now what are some examples of IV data that is continuous? I'll give you some in just a minute, all right? You can't use a line graph. You have to use a bar graph instead if the independent variable data is not continuous. And I'll give you some examples of that. All right, so continuous data. Continuous data means that the numbers that you could get could be anything between any of the numbers you actually have. So for example, you could weigh 100 pounds, 101 pounds, 102 pounds, 103 pounds. Weight is continuous. You could be 5 foot, you could be 5'1", 5'2", 5'3". Height is continuous. Age, you could be 1 year, 2 year, 3 years. Time, amount, these are all what we call continuous data. That means you're allowed to use a line graph. You can put little points and you can connect them with a line. Okay? The reason why the data is continuous is because there are actually numbers between the points you've actually measured. Okay? Now, discontinuous data is stuff like people or places or assignments or colors. Okay? So let's say I was making a graph of everybody's score on the first test. So I have people, your names across the x-axis, and then I have test scores going up and down on the y-axis. Okay, so let's say I have Mary and Bob. Okay, so Mary got her score and Bob got his score. All right, there's nobody between Mary and Bob that's a real person. So I could put in a bar, but I can't connect those two data points. That would be incorrect. Okay, so discontinuous data is when there's nothing that's real between the points. Okay, hoping that makes sense. All right, so all graphs start with two arrows, one pointing left and right and one pointing up and down. Okay, we always call the horizontal line the x-axis and the vertical line the y-axis. You probably got this in algebra, okay? Math uses the exact same rules, okay? X is horizontal, Y is vertical, okay? The independent variable, the numbers that you have from your table for your IV always will go across the x-axis. That's where they're placed. And the DV always goes up and down on the y-axis, okay? So we will stop there. Thank you for listening. And I will talk to you guys later. All right.